Stanford University.
We do know a highly accurate description of elementary particles. It has a lot of parameters. Depending on the particular version of it, which turns out to be true, it could vary anywhere from 25 parameters to 150. But of order, somewhere's like 50, 75, 100 parameters, numbers. What kind of numbers? The masses of quarks, the masses of electrons, the masses of muons, the coupling constants, the value of the electric charge of particles, all kinds of things like that. And in addition, just a list of what the particles are. Some of the particles are related to each other in various kinds of mathematical ways. Others of them are not particularly simply related to each other. And so there's a very accurate theory that describes everything basically that's known about elementary particles. Thousands of experiments. In principle, it can explain nuclei. It can certainly explain atoms. Quantum electrodynamics is part of it. And therefore, it can explain molecules and chemistry. Of course, when I say it can explain it, I mean to say if you had infinite computing power, that you could solve its equations and do it with reasonably high precision. You could explain chemistry, molecules. I'm not going to tell you could explain life. That I think I would get all sorts of reactions to. That's a separate issue. Consciousness and so forth. Leave that off the table. Then in addition, we have a theory of gravity. Oh, of course, the theory of fundamental particles is quantum mechanical, heavily quantum mechanical. We also have a classical theory of gravity, Einstein's field equations, general relativity. Again, it's a highly accurate theory. Does it have any parameters in it? Well, it has Newton's constant. It's worthwhile spending a few minutes asking what the fundamental quantities are in physics. There's all sorts of quantities like the mass of the proton, or more exactly, the ratios of masses of particles, ratio of the mass of the proton to the mass of the electron. All those are parameters. They're not thought to be highly, deeply fundamental. They're not universal parameters. They're specific parameters that have to do with the proton and the electron in this case. If I was to substitute for the proton some other similar particle, the neutron for example, and substitute for the electron the mu particle, which is very similar to the electron, would be an entirely different ratio. Where they came from, why they're there, what they reflect, we don't really know, but they don't seem to have any really broad generality. There are a couple of parameters, 3 of them to be precise, which have great generality, and I'll explain what I mean by generality and universality. First of all is the speed of light. In what sense is the speed of light universal? Well, when you think about what Einstein's principle says, it says that all matter and all information moves with less than the speed of light. The key word there is all. Whenever you have one of these statements that all such and such and such and such and such and such, some law of physics, when that word all is there, you know that it has to do with something deep and fundamental and universal. So there's the speed of light. See. Next, Planck's constant. Is Planck's constant just some random number that has only to do with one specific kind of phenomenon? Or is it, again, a universal quantity? Well, in this case, it's the uncertainty principle. The uncertainty principle says for all particles, and not only particles, for all objects, period, the uncertainty in the position times the uncertainty in the momentum is always greater than or equal to h bar. Again, the word all comes up repeatedly in that sentence. And so h bar, Planck's constant, is also a very fundamental constant. And fundamental in the sense of universal, governs all phenomena, not just some specific particular kind of particle, but all particles, all objects, period. And finally, there's Newton's constant. Remember Newton's law of gravity? All objects attract each other with a force that is inverse to the distance between them, inverse squared to the distance between them, and proportional to the product of the masses times a constant called Newton's constant, capital G, that is the same for all possible objects. When a little bit of relativity is added in, mass becomes energy, and so all forms of energy attract each other, but the universal constant G is always there. So this use of the word all in the laws for which these things are the numbers associated with them is apparently deep. Planck was really the first one to realize this. He was the first one to realize how fundamental. Now, at that time, he didn't even know what h bar really meant. He had parameterized radiation, thermal radiation, black body radiation, by this quantity h bar. He didn't really know what it meant. He didn't know what quantum mechanics was going to be, that it was going to be a whole new way of thinking about things. He just had discovered this new constant, which together with C and G gave three constants of nature. And ultimately, of course, we did find out that these three constants are deep and fundamental and universal, but Planck sort of suspected it. And the other thing he realized, which is also very important, is that there are three dimensional units in physics, which are the three basic dimensional units that we work with. One of them is length. One of them is time, units of length, units of time, and units of mass. What he also realized is that the units of C, h bar, and G was such that you could combine them and make units of length, time, and mass. So that means that there's some fundamental, if there are fundamental constants here, and these constants, incidentally, carry dimensions. They're not dimensionless. They're not like ratios of masses, which are dimensionless. They carry dimensions. The units of length, time, and mass also carry dimensions. And what it meant is you could make up, not make up, you could derive a basic unit of length, a basic unit of time, and a basic unit of mass from these three quantities. Shall we do it? Okay. It's called dimensional analysis. The first thing we have to find out is what is the units of C, h bar, and G. Here's the way you do dimensional analysis. You first make sure you know what the dimensions of the quantities that you're dealing with are. And the symbol for the dimension of a quantity is just a square bracket like this. This doesn't stand for the speed of light, it stands for the dimensions of the speed of light. All right, what's the dimensions of a velocity? Length over time. So that's length over time. All right, what's the dimension of Planck's constant? The dimension of Planck's constant, h bar. 1 over what? Probably right, but I have to do it. Let's see if we can figure it out. We need an equation that involves h bar. The basic equation that involves h bar always involves distance times momentum, right? Uncertainty principle. Distance times momentum. All right, so the units of h bar are the units of length times momentum, but momentum is mass times velocity. So it's mass times velocity, and a velocity is another L over t, so that's L squared over t, and I think somebody said that. Length squared mass over time. I don't know how you knew that so fast. How did you know that so fast? Memorize it? Who did it? Some guy back there, okay. Mass squared, okay, there we go. And finally, Newton's constant. All right, we need a formula that involves Newton's constant. Why not take the basic formula that Newton started with? Force is equal to mass times g divided by distance squared, right? R squared. Okay, well, we're not quite finished because we have to we have to know the units of force. We're trying to find the units of g. What are the units of force? Well, we use another Newton equation. Mass times acceleration. Mass times acceleration. We can cancel. We're only interested in the units now. All right, we can cancel a mass from both sides. What about an acceleration? An acceleration is a length divided by a time squared. Right? So this is a length divided by a time squared. This is, oh, good, thank you. Length divided by a time squared. This is a length squared here. So let's multiply by a length squared. This will give us a length cubed on the right side, and we'll get rid of the length squared on the right, left side. Length cubed divided by time squared is equal to m times g. And now to find g, all we have to do is divide by a mass. The meaning of this equation here is that the units of g are units of length cubed divided by mass divided by time squared. Okay? All right, now I want to build, out of h bar, g, and c, I want to build a length. I want to build a quantity with the units of length and see how small or how big it is. So what do? Standard method for doing dimensional analysis is you say, I'm interested in some length. Let's call it L. It's the basic length that I can build out of these quantities. And it's c to some unknown power. I don't know what power to put there to begin with. H bar to some other unknown power. G to yet some other unknown power. And then we simply stick in these units and make sure that what's on the right side and the left side both have units of length. Okay, so let's put that in. C to the power A is a length to the power A divided by a time to the power A. H bar to the B is a length to the 2B, a mass to the B, and a time to the B. And finally, G to the C, that's length to the 3C divided by mass to the C divided by time to the 2C. Right. And this whole has to work out to be a length. Okay, I used capital L here. I should have used small l. This all has to add up to a length. Okay. So what's the first thing I can conclude? I got to get rid of the masses and the times and only be left with a single power of length. So in order to get rid of the masses, I had better have that B is equal to C. That's my first conclusion. So why don't we stick that in? Let's put in everywhere we see it. Let's put in B is equal to C and use it. All right, so let's see. Wherever we see C, we can put B. To B. And the masses now automatically cancel, so I can get rid of them. Now I want to get rid of the time. So that means what? That A plus B plus 2B has to be 0. It should be time to the 0. Say it again? To 0. There's no length, there's no time on the right-hand side. So all right, so that says that a plus 3b should be equal to 0. And we've got to get a single power of length on this side. So that looks like it says that a plus 5b, I hope this works. A plus 5b, I don't recognize it at all. A plus 5b should be 1. A plus 5b should be 1, so on that side. Now we should be able to solve these two equations. The first thing to do is to subtract the first one from the second one. We get rid of a, so that gives us 2b equals 1. Yep. And b equals a half. Yep. B equals a half. And then what about a then? B is a half, so a is equal to minus 3 halves. Yep. A equals minus 3 halves. And of course, c is the same as b, so c equals b. Okay, now we can write down our unit of length, the fundamental unit of length now, which is the speed of light c to the a is equal to minus, was it minus 3 halves? Did I get that right? Let's write L squared to the 2a, 2b, 2b. I don't want to write I don't feel like writing square roots. 2a is minus 3. So that's c cubed. No, c to the minus 1 over c cubed. 1 over c cubed. H bar to the 2b. 2b is 1. H bar. And g is also 1, sorry, b is also 1/2, so it's just g upstairs, right? Thus, the basic unit of length, the fundamental unit of length that you can build out of these is equal to the square root of h bar c over h bar g over c cubed. All right, the next thing, of course, now is to ask how big is this length? How big is this length? And Planck did ask that. So we stick in, anybody know what h bar is in metric units? I can never remember. Right. It's a very small number, right? G is a rather small number, 6.7 times 10 to the minus 11. H bar is 10 to the minus what? 10 to the minus 30 something. And c is a very big number, so altogether, this is a very small number. Well, it's a little bit less small because you have to take the square root of it, but it's still pretty small, and this is about 10 to the minus 35 meters. That's the Planck length. That is the Planck length, 10 to the minus 35 meters. And given that c and h bar and g are such universal things that govern so much, measuring masses, measuring lengths in units of this Planck length must mean something fundamental. Okay. That was Planck's. All right, let's do the time unit. The time unit is obvious now. There's a unit which is 10 to the minus 35 centimeters, and it's very clear that the time that's associated with it, here's my fist, it's 10 to the minus 35 centimeters. How long does it take light to travel across it? Light travels at 3 times 10 to the 8th meters per second, so we have to divide this number by 3 times 10 to the 8th. All right, so the time, corresponding time is equal to 10 to the minus 35. And when I say 10 to the minus 35, there's some numerical factor in front of it. 10 to the minus 35 times, divided by 3 times 10 to the 8th. All right, so let's put a 10 to the 8th here and another 3. 35 and 8 is what? 43. All right, so this is of order 10 to the minus 43 seconds. That's the Planck time. But of course, all it really is the time that it takes to travel by light across the Planck distance. So it's not a new thing. And what about the Planck mass? Let's do the Planck mass. How can we get a mass out of this easily? How can we get a mass without doing any work? Let's see. What's that? Say it again. Oh. Here's the way we do it. We use quantum mechanics to relate energy and time. Energy is mc squared. Okay? So energy times time, which is mc squared times time. That's energy times time. That should have this. That should be like Planck's constant, right? Energy times time has the same units as Planck's constant. All right. So energy is mc squared times time, and that should be like Planck's constant. Equals here simply means has the same units as, but that means that we can construct a mass by taking Planck's constant and dividing it by the speed of light squared times the Planck time. Let's call it the Planck time. We know what the Planck time is. The Planck time is 10 to the minus 43 seconds. So there's a small number now in the denominator. A very small number in the denominator, a very small number in the numerator, another big number in the denominator. What do you get? You get a number which is neither terribly small nor terribly big. It's about 10 to the minus 8th kilograms. That's not terribly small. The Planck mass is about the mass of a dust mote. If you ask how much energy it is, how much energy would be released if you could turn all of that energy, all that mass into energy, you have to multiply it by the speed of light squared. Speed of light squared is about 10 to the 17. So 10 to the 17 times 10 to the minus 8 is 10 to the 9th or something? Did I get that right? 10 to the 9th what? Joules. About a tank of gasoline. So I figured once that you could drive across the country with my old first car, a Ford. I still have a Ford. With my old first car on about 10 tanks of gasoline, which meant 10 Planck masses, which meant about 10 to the minus 7th kilograms. 10 Planck masses, you could drive across the country. How did I get on that? Why did we get to that? That's the Planck mass, energy, all the same thing. Yeah. What do we know? Yeah. Okay. Now, the point is that this length scale, 10 to the minus 35 centimeters, is how much smaller than the scales that we probe, let's say at the LHC. The LHC probe scale is about 10 to the I want to say 10 to the minus 17th centimeters. But whatever that distance is, I do know that distance in Planck units. The distance that is probed in Planck units is huge, of course. The Planck unit is very small. The distances that are being probed at the LHC are about 10 to the 17th, 10 to the 17th Planck, 10 to the 17th, something like that, about 10 to the 17 Planck lengths. Okay, 10 to the 17th is a gigantic number, and it means that the size scales that we're probing are huge by comparison, 17 orders of magnitude bigger than the Planck scale. It's like the whole universe compared to a pea, if I'm not mistaken. Well, I'm not sure that's exactly right, but it's a very discrepant length scale. And what don't we know? We don't know everything in between. All right, so as I said, we know that which we know is a lot less than that which we don't know. That's the entire range of phenomena. Nevertheless, if we look at the phenomena at that scale that the LHC is probing now, it looks like the standard model of particles is a highly accurate thing, but perhaps it's not too surprising that given that it's something that may have to arise somehow from 17 orders of magnitude, possibly different things going on between those two, not too surprising that there are a large number of parameters that are necessary in the standard model. It's just like nuclear physics. Nuclear physics takes place at a bigger scale, and again, you need even more parameters to describe nuclei because they're complicated. The objects that we're studying at the LHC are probably rather complicated, probably not the fundamental basic units of anything. And so, as I said, we don't know everything in between. The question of why the parameters are what they are, and in particular, certain of the parameters which are highly fine-tuned and seem to have to lie in very, very narrow ranges in order to make the world be anything like what we see, those again are completely mysterious from the point of view of the mathematics of the standard model of particle physics. We don't know why they are what they are.
I read that the recent results show that the Higgs boson is turning out to be lighter than expected. Is that
actually heavier than expected?
Heavier than expected. Does that expose?
Well, no. Heavier or lighter than expected when? I mean, there was a time when it was thought to be very heavy. That was a long, long time ago.
There's definitely new physics somewhere that keeps it to be as light as it is.
Oh. Yeah. That's something I was heavily involved in the 80s, earlier, the 1980s, late 70s. Yeah, we don't understand why the Higgs boson, okay, so when I said as heavy as it is, as light it is, there's two things going on. The first question is, why are any particles, where did we put the Planck mass? Here's the Planck mass. That's a big, heavy mass. I mean, on the scale of particles, elementary particles, this is a real giant mass. Okay, many, many orders of magnitude heavier than electrons or anything else. First question is, why do any of the fundamental particles, if they're really fundamental, why are they so much lighter than the Planck mass? Why are there any particles which have masses 10 to the minus 20, 10 to the minus 25, 23, whatever it is, 10 to the minus 22 Planck masses? That would be the electron. 10 to the minus 19th Planck masses for a proton. Quarks, somewhere in between. Why are any of the particles so light? It all traces to the properties of the Higgs boson, why the Higgs boson is so light. Why is the Higgs boson itself so many orders of magnitude lighter than the, you read in the newspaper that the Higgs boson is the fundamental particle that makes the world work. Why doesn't it have this mass if it's so damn fundamental? And the answer is, you can make it be anything you want by tuning the parameters of the theory. There are parameters in the theory, and if you tune them in various ways, you can make that Higgs mass anything you want. But if you tune it crudely, with crude tuning, you're going to get this answer. If you tune the parameters in one range, you'll get this answer with a positive sign. If you tune the parameters the other way, you'll get it with a negative sign. On a tiny, tiny little knife edge of parameter space, you can get the Higgs mass to come out to be what it's observed to be. Unless there's other physics going on other than the standard model. So given that the Higgs mass is as light as it is, people have invented explanations of why it's so light, but they tend to overshoot. They tend to overshoot. The standard explanation of why the Higgs mass is so light is called supersymmetry. We're not going there, but I've been there. And in the simplest supersymmetric models, it tends to overshoot the mark. And you, instead of getting a mass of 125 GeV or whatever the right number is, it comes out to be about 100 GeV. That's a significant difference. That's a very significant difference. So it's both too light from one point of view, but then from the overshot theory, which tends to make it even lighter than it is, it's a little too heavy. So that was my funny answer when you said it was too light. I said it was too heavy. Yeah.
How does the Higgs get mass to the other particles?
I think I gave a lecture on it about a year ago, and I think I remember seeing you in the audience. Yeah, I remember it. And it's still on the internet.
So I believe from that lecture, you said the Higgs is what makes all the quote normal particles have any mass at all.
Not the proton and neutron.
Okay.
Yeah.
So would we expect the WIMPs or whatever, the dark matter particles to have order the Planck mass or more?
Well, WIMP stands for weakly interacting massive particle. Weakly interacting means that it has cross-sections and properties consistent with the weak interactions. Now, the reason people want it to be a WIMP is because they want to be able to discover it in the laboratory. If the cross-sections and interactions with ordinary matter are much, much less than what is called weakly interacting. Weakly interacting is not a generic term. It means some special number. If the cross-sections for scattering, if the influence and the interactions with ordinary matter are too weak, you'll never discover it. If it's in the range that people call WIMPs, then the various constraints of cosmology, particle physics, and a number of other things tell you, no, those WIMPs on the Planck scale mass, the Planck mass scale, will still be very light. They'll be heavier than the proton by a factor of 1,000 or something like that, or maybe 10,000, but they won't be Planck scale. On the other hand, if you allow them to be arbitrarily weakly interacting, so that we will never be able to discover them, then the mass of those things could be anything. And so part of the set of assumptions that goes into many, many papers on WIMPs is that they're in the range that can be discovered. Yeah.
Yeah, Planck constant, Planck mass, Planck time are fundamentally the smallest units of its type.
What?
Planck time, Planck length, Planck's constant are fundamental units. They're like the building blocks, but a Planck mass seems, what is the semantics of it? What does it signify?
It's the mass of the smallest black hole. That's what it is. It's the mass of the smallest possible black hole. What is it? Why? Why black holes? Well, it contains G. You know that black holes have entropy. They have information content. Their information content is proportional to some of these constants. The information content of the smallest black hole is 1 bit of information. In Planck units, it has an area of its horizon, which is 1 unit in Planck area. If you ask what its mass is, the mass of the smallest possible black hole, it's basically 1 Planck unit. So that's what it is. Yeah.
So does that mean that there's a sort of does that mean there's a fundamental energy content to 1 bit?
Yes. Yes. The Planck unit, yeah.
So,
Now, there can be particles which are lighter than that, but they're not black holes, and they don't carry the same kind of information. Yeah. There's an energy content in a sense to a single bit of information.
and that's the Planck mass?
Mm-hmm. That's not to say there can't be things which are lighter, but they won't be the same kind of things. Okay, are we ready to start the cosmology for the evening? Yeah, that's good. You know, from now on, I could set C and H bar and G equal to 1 and say we are working in Planck units. And Planck units, where the Planck length scale is 10 to the minus 35 meters, the Planck time is 10 to the minus 43 seconds, and the Planck mass is 10 to the minus 8 kilograms. If you go back and you ask what is C, H bar, and G, they're all equal to 1. So physicists often tend to work in Planck units. And in fact, I remember all sorts of orders of magnitude, relations between units, by remembering what they are in Planck units. It's and I transfer back and forth from various units of ordinary physics, laboratory physics, by first remembering what they are in Planck units. It's easier to remember one set of units and then stick to that. Yeah. Okay, so let's begin with the map of the universe, which I think I sent over the internet and which most of you have seen. Where's the eraser? No eraser? On the table. All right, and the map is called WMAP. W is somebody's name, Wilkinson, but WMAP is a map of the sky in the microwave, and what it's looking at is the thermal remnant microwave radiation that we've talked about earlier, coming from the era of decoupling. When we look back, here we are, different shells. And the furthest out shell that we can see is the shell where the universe became opaque because it was ionized. Okay? Out there is the furthest shell we can see, and we don't really see it through a telescope. We see it through microwave detectors. And the radiation from from those places here has been redshifted by about a factor of 1,000. It started out as, roughly speaking, ordinary light, maybe a little hotter, and arrives at us at 3-degree blackbody radiation.
Could you say exactly what that map?
What?
Or maybe you-
No, we're going to talk about the map, yeah.
I mean,
All right, right.
Units and that sort of,
Hmm?
like the direction it corresponds to and the length scales. or-
Yeah. Okay. Right. So if you look around and with a infrared, not an infrared, a microwave telescope, and you point it in different directions, you pick up this radiation. And the radiation is very isotropic. The temperature in every direction is about 2.7 degrees. And to very high precision, everything is very, very isotropic, to very, very high precision. Perfect isotropy would also mean perfect homogeneity for the universe. The universe is not perfectly homogeneous. And if it was perfectly homogeneous in the end, it would remain perfectly homogeneous. So there must have been some, at least very small inhomogeneities. Small, I don't mean small in size, I mean small in magnitude. Small inhomogeneities. So you look out at the universe in different directions, and this oval, that's just a projection onto the plane of all directions. This point over here is the same point as this point over here. There's the northern half, the southern half. The north half is not the same as the southern half. And what does north and south mean? It's plotted in such a way that right down the middle here is the galactic plane. We are sitting in the middle. We're surrounded by a galaxy. We look out in all possible directions, and of course what we see is the galaxy. In some directions, the galaxy is very, very dense. Other directions, not so dense. So the center of the galaxy is placed at the center here. All right, these points here are looking away from the galaxy. That's looking straight at the center of the galaxy. This is looking up above, to the north of the, it's called the north. I'm not sure if it's really north. It is, It is, it is, it is, it is. It is toward the north. This is the northern hemisphere, this is the southern hemisphere, and that's the whole 4 pi solid angle that astronomers can see. What we're looking at now is not stars and galaxies and so forth, although stars and galaxies could be plotted on exactly the same thing. We're looking at the microwave background. And the first approximation, what's seen for that microwave background, well, there's a band across the center because we see microwaves coming from the plane of the galaxies. These people are very, very clever and they know how to subtract it out. So after it's been subtracted out, what's seen is extremely featureless, extremely isotropic, indicating that the universe is isotropic around us and therefore rather homogeneous. Okay, but as I said, something accounted for the fluctuations or the ripples and so forth, which led to galaxies, clusters, superclusters. Remember the pictures we drew last time of caustics at the bottom of the swimming pool? Caustics at the bottom of the swimming pool come from little surface ripples at the top of the swimming pool. And so in going from the top to the bottom of the swimming pool, if the swimming pool was perfectly flat on the top, it would be no caustics on the bottom. The fact that we see structure, galaxies forming these intricate patterns, means that those patterns must have been there at least in a very, very weak form to begin with. The WMAP map is exactly a map of the temperature distribution, okay? Now, the temperature distribution is very close in all directions to that good old 2.7, whatever it is, Kelvin, but it varies a little bit. And in fact, the variations in the temperature, the fluctuations in it, meaning to say the inhomogeneities, divided by the average temperature itself, are of order 10 to the minus 5. 1 part in 100,000. That's very difficult to detect, obviously. Anything that's 1 part in 100,000 is hard to detect. But when I say that that's true, let me tell you 2 places that number came from. One place that number came from was from the known distribution of masses in the universe, traced backward when cosmologists asked how much variation would there have had to been at decoupling in order that it would have evolved into what we see today. The technology for doing simulations today is very good. In those days it was less good. But nevertheless, there was enough technology in the form of simulations, both analytic and computer, 25 years ago or something like that, maybe a little more, that it was pretty clear that there had to be local fluctuations of roughly this big in order to translate into what we see today. Okay. The other place that it came from is direct observation. The Wilkinson map is a direct measurement of the temperature distributions over here, and it doesn't look, on the scale of 10 to the minus 5, you have to escalate everything up by 5 orders of magnitude, and then you see this blotchy and the interesting thing about the blotches is you see structure on all scales. Some places a little hotter. I can't remember now whether the hot is blue or the hot is red. I don't remember. Smaller scale structures, bigger scale structures, big giant structures, structures within structures, and essentially at every scale you see features, blobs. It's kind of a fractal. In fact, if you looked at it and you blew it up, it would look exactly, well, it would look largely exactly the same. It's more or less scale invariant with a temperature fluctuation. Each one of these fluctuations is about 10 to the minus 5 of the background average density, average temperature. Now, where do temperature fluctuations come from? Temperature fluctuations come from mass distribution fluctuations. Fluctuations, I mean, variations across the sky. If let's imagine that there was an excess of mass in this little region over here. Not a huge excess of mass, a small excess of mass. Then light coming out from there would be redshifted more than it would be from other places. If you have a lump of mass and light is escaping from it, the light has to extract itself and get away from that mass, and it loses energy. In losing energy, the temperature, the apparent temperature in that direction will be less than the temperature in some region where there isn't a mass excess like that. So these temperature fluctuations have to do with mass distribution fluctuations, and this translates into the statement that at that time, the variations in the energy density divided by the average energy density, this is at the time of decoupling, was also about 10 to the minus 5. So we need a theory to tell us where this came from. This sounds like a tall order to explain at the very beginning of the universe where such things came from. Oh, incidentally, there is a pattern, and as I said, the pattern is this scale invariance. It looks the same if you blow it up or if you shrink it down, that is the primary pattern. Okay, what?
I was wondering, since the light is from that recombination, wouldn't the slight inhomogeneities just be from just that last scattering?
You mean just from microscopic fluctuations?
Yeah.
Oh, that wouldn't be on this scale. These are huge scales.
Oh, okay.
Right. Such scales at the time of decoupling would have corresponded to very, very large things. So it's not microscopic things. Right. But perhaps if you traced it backward, even past that, perhaps it does have to do with microscopic things. And in fact, that is exactly the theory of these fluctuations, that they originated from quantum fluctuations. Quantum fluctuations plastered across the sky are what the current theory is of these fluctuations. Now, we're not going to get to it, but the theory I'm going to tell you about is a very high precision theory. It is explained to extremely high precision, a huge amount of data. So I don't think anybody these days has any doubt that the blackboard can be raised. Ah, there. Jesus, that's hard. Okay. So what is a theory? To understand the theory, you have to understand only two things. You have to understand quantum fluctuations, quantum zero-point motion of a harmonic oscillator, and you have to understand the damped harmonic oscillator. The damped harmonic oscillator. And you need to know the equations of a scalar field in the expanding universe. Let's go through the damped harmonic oscillator first. Do it over here. All right, let's start with the undamped harmonic oscillator. That's just a good old harmonic oscillator where the energy, or the Hamiltonian, whatever we want to call it, is x dot squared, the kinetic energy squared divided by 2 is the usual convention, plus omega squared, where omega is the frequency of the oscillator, times x squared divided by 2. Incidentally, on the average, as the oscillator oscillates back and forth, potential energy becomes kinetic energy, becomes potential energy, becomes kinetic energy. But the time averaged kinetic energy and potential energy are the same. It just transfers them back and forth, but the time on the time average splits them pretty much equally. In fact, splits them exactly equally. Next statement, quantum mechanically, the energy of an oscillator is proportional to an integer plus 1/2 times h bar omega. The integer counts up how many units of excitation there are. It really covers how many units of excess energy has been pumped into it. This 1/2 here is the 0-point energy. The origin of 0-point energy is the uncertainty principle. A particle cannot have simultaneously a known position and a known velocity. And for that reason, both x and x dot cannot be 0 in the ground state of the harmonic oscillator. And you have to sort of make a compromise. And the best compromise, consistent with the uncertainty principle, says that even in the ground state, the harmonic oscillator oscillates and has a certain amount of energy, and that's that 1/2 h bar omega here. The 1/2 h bar omega corresponds to an oscillation. It corresponds to a small oscillation. And if you want to know how big an oscillation it is, how much does x vary going back and forth during these 0-point oscillations? All right, so the ground state energy, ground state meaning when the oscillator is absolutely unexcited, is 1/2 h bar omega. I told you a moment ago that on the average, this and this are the same. So therefore, we can write that on the average, time average, omega squared x squared divided by 2 must be the same as 1/2 h bar omega. Now this is only half the energy. Half of it is here, half of it is here. So in fact, this should be 1/4 of this. Or omega squared x squared is 1/2 h bar omega. And now we can read off how big x squared is. X squared, or x let's take, x squared will be of order 1/2 h bar over omega. Let's forget the factors of 2, they're not important in this. X squared will be about h bar over omega. And that's about how far back and forth the oscillator oscillates due to 0-point motion. And notice it's small. It's small because h bar is small. Okay, what about this one over here? Let's, okay, that's really good enough. How does x oscillate? It oscillates either like a sine wave, like a sine of time or a cosine of time, or we can write it as x is equal to this times e to the I omega t. This is how much it oscillates back and forth, and this just represents the oscillation. Oscillation going from -1 to +1. The e to the I omega t is a way of writing sines and cosines of omega t. What about x dot? Let's calculate x dot. If this is x, then to find x dot, we just differentiate e to the I omega t, and that gives us a factor of omega. So x dot will be proportional to omega times this. Omega times that will be square root of h bar times omega. If I multiply 1/square root of omega by another omega, it will be square root of omega. And how about x dot squared? X dot squared will also be h bar omega. And that's just a statement that there's a factor of 2 someplace. But that's just a statement that both terms in the energy will be about comparable and both equal to h bar omega. So that's the theory of 0-point oscillations of a harmonic oscillator. They're always there. You can't get rid of them. No matter how much you cool the oscillator, no matter how much energy you try to take out of it, they're always there. Now let's go to the damped harmonic oscillator. The damped harmonic oscillator has another term in it. Another term in its equation of motion. I didn't write the equation of motion. Let's write down the equation of motion over here. The equation of motion is x double dot plus x times omega is equal to 0. This is acceleration. If we put x omega on the other side, if we put x omega on the other side, it would be the restoring force. And omega would be the spring constant, right? Omega squared, I'm sorry, omega squared. Omega squared. That's what you get from this, omega squared. Omega squared would be the spring constant pulling it back. So spring constant is omega squared, and that would be the equation, and it would give you oscillations going back and forth. The damped harmonic oscillator has another term, the damping term, and it corresponds to friction. Friction or viscosity. What is this? This is a spring with a rock on the end of it, vibrating back and forth in honey. Everything is surrounded by honey, so it's in a viscous fluid. The viscous fluid exerts viscous forces, and with viscosity, the equation is x double dot plus, what did we call the viscous drag coefficient last time? I don't remember. I think, C sub d. Well, we're going to call it gamma tonight. Gamma stands for viscosity. Gamma times what? X dot plus the restoring force equals 0. That's the equation of motion of a damped harmonic oscillator. And let's solve it. This kind of equation, if you know anything about differential equations, you look at this equation and you say, aha, linear differential equation of second order with constant coefficients. Can you say that? Linear differential equation, first order with constant coefficients. And that signals that the solutions have the form of exponentials of time, e to the alpha times t. Times coefficients. You can put numbers in front of them. That's the kind of solution, general solution, numerical constants times e to the alpha t, where alpha is a number which depends on gamma and omega. Okay. Let's see if we can find out what alpha is from the equation of motion. All we do is plug in. This is x. X equals this. X dot is equal to alpha e to the alpha t. And x double dot is equal to alpha squared e to the alpha t. And so if I plug into this equation, I will get alpha squared plus gamma alpha plus omega squared all times e to the alpha t. Each one of these is multiplied by e to the alpha t. I'm not going to write the e to the alpha t. Just imagine that it's there for a moment. And we're going to set the answer equal to 0. That's the equation of motion. Well, e to the alpha of t, e to the alpha times t is an exponential. It's not 0. The only way we can get 0 on the right-hand side is if the thing that multiplies e to the alpha t is 0. So this gives us an equation for what alpha is. Given gamma and given omega, numbers, numerical constants, alpha is determined by a quadratic equation. So let's solve it. Alpha is equal to minus gamma plus or minus, there are two solutions, plus or minus square root of gamma squared plus 4, yeah, minus 4, let's see, where did,
Minus 4 gamma squared. Omega squared.
it has to be minus. Over 2. Yeah, b squared minus 4ac, sure.
If gamma's a positive number, shouldn't the equation be minus gamma, x dot?
Hmm?
The original equation you're solving,
Yeah.
if gamma's isn't the viscous force opposite the direction of the?
Yes?
So gamma's a negative number?
No. No. F equals ma. Here's A. If I want it to be equal to F, I have to put this on the other side. Okay? So it will be gamma, right. 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 All right, so this is alpha. You can first of all see that for every gamma and omega, there are two possible alphas. That means the general solution will be a coefficient times e to the one of the alphas times time, and then another coefficient times another such term with two different coefficients. Okay, so let's see what we make of this, and let's study it in various regimes of the parameters. First, let's take the case where viscosity is negligible or small. When viscosity is small, and that means in this case gamma squared smaller than 4 omega squared. In other words, the situation where what's inside the square root is negative. In that case, the square root is imaginary. Okay? Square root of a negative number is imaginary. So for gamma squared less than 4 omega squared, that's weak viscosity and a pretty good restoring force. In other words, when the restoring force is strong and the viscosity is weak, what do we expect to happen? We expect it to oscillate like an oscillator pretty much. Okay, so let's see, so what do we get? In that case, we write that alpha, since what's inside the square root is negative, we can write it in a different way. We can write it as minus gamma over 2 plus or minus 1/2, and let's write it now as I times the square root of 4 omega squared minus gamma squared. Instead of writing gamma squared minus 4 omega squared, I've written 4 omega squared times gamma squared, but then we would have to put a minus 1 inside the square root, and a minus 1 inside the square root means an I outside the square root. Okay, so there we are. There's our alpha. And now let's look at the solution. Where is our solution? E to the alpha t. The general solution is x is equal to one coefficient, a coefficient, times e to the minus gamma over 2t times e to the plus or minus I over 2 square root of the same thing. When gamma is small, this is basically 4 omega squared minus a little bit. Square root of 4 omega squared is 2 omega. 2 omega divided by 2 is, do I have that right? Yeah. So, oops, times time upstairs in the exponent. This is basically e to the I omega t, the good old oscillation, except that the frequency is a little bit less because of the gamma. On the other hand, on top of that, there's a multiplicative e to the minus gamma t, which means that the solution oscillates but slowly dissipates. That's the damped harmonic oscillator. And the regime where gamma squared is small compared to 4 omega squared is called the underdamped oscillator. It's underdamped, which means that the damping is not strong enough to prevent it from oscillating. All right. If you take a harmonic oscillator and you try to make it plow through concrete, it's not going to oscillate. So that becomes the overdamped region. Let's do the overdamped region. The overdamped region is when it's underdamped, now overdamped. That's gamma, that's a lot of viscosity, and a lot means bigger than 4 omega squared. In that case, let's just do that case over here. In that case, we get rid of the I and write it as gamma squared minus 4 omega squared, the same way it was over there. Gamma squared minus 4 omega squared is a positive number. Alpha, there are two solutions for alpha, two roots of this equation with a plus or minus. Both of them are negative. Both of them are negative. You can see that this is obviously negative. Okay? Now, you have two possibilities. You can add a positive number to the negative number, but what's in here is gamma squared minus something. So this is less than gamma squared. When you take its square root, it's less than gamma. So therefore, even with this term, adding in the 1/2 square root here still leaves you with a negative number. If you put it in with a minus sign, it's surely negative. Even if you put it in with a plus sign, it's still a little bit negative. So there are two solutions, each of which goes like e to a minus an alpha t, where alpha is the absolute value, alpha is always negative. That means each of the solutions decays with time. The general solution is the sum of two decaying solutions, and that's the overdamped case. It doesn't oscillate, it just exponentially drops off and goes to 0. Okay, okay, that's the overdamped case. And now there's a transition between them. The transition between the overdamped and the underdamped is interesting, and we'll call it the critical case. The critical case is right on the border between them, and it clearly is defined by gamma squared equals 4 omega squared. All right, so critical damping is when gamma equals 2 omega. It tries to oscillate, but it doesn't quite oscillate very much, and it goes to 0, but not before maybe it makes half an oscillation or something. That's the critical damped case. And one more case. All right, that's a transition. That's a kind of, or a crossover. We would call it a crossover, going from overdamped to underdamped. Behavior changes, not radically at that point. It just smoothly changes, goes from one behavior to another. And one more behavior I want to consider, and that's the case when the restoring force is 0. That's when gamma is much bigger. That's completely dominated by friction. Completely dominated by friction, and the restoring force is 0. To get that case, let's go back to the equation. We don't need to deal with it. We can deal with the solution, but it's easier to just go back to the basic equation. Now we're not doing gamma equals 4 omega. Let me put this here. This is the transition between the two behaviors. It should be 2 omega. We took a square root. Okay. With omega equals 0, our basic defining equation for alpha is that alpha squared plus gamma alpha is equal to 0. Or that alpha times alpha plus gamma is equal to 0. If a product of two numbers is equal to 0, then one of them better be 0. Both of them can be 0 too, but you can't simultaneously have alpha equals 0 and alpha plus gamma. Right? So there are two solutions, alpha equals 0 and alpha equals minus gamma. What does that mean? Alpha equals 0 is a solution e to the alpha t with alpha equals 0. What's e to the alpha of t with alpha equals 0? 1. But of course I could have put a constant here. So let's call that c, c0. Any constant times e to the alpha t with alpha t just being 1, plus another solution, which is c1, let's call it, e to the minus gamma t. That's the case where alpha is equal to minus gamma, e to the minus gamma t. What is this thing? This asymptotically at late times just goes to a constant, but it goes to a constant exponentially. What this is doing is it's the stone moving through the viscous fluid, no gravity, no forces on it. You give it a push, and it just exponentially comes to rest. And it comes to rest at what point? It comes to rest at point C0. We've parameterized it so that it comes to rest at point C0. When time is large, this is negligible, and so it just comes to rest at some constant. That's the case with no restoring force. Now what is it? Okay, so you have the three situations. Small gamma, large restoring force, oscillations, which slowly die out. Critical damping, let's not worry too much, that's the crossover. It's important to know where the crossover is. And beyond the crossover, it just dies quickly. It just really dies quickly with less than a single oscillation. Comes back to zero. But the final case, no restoring force at all, it just comes to zero. It comes to rest at an arbitrary position, depending on the initial conditions. You give it a push, there's no restoring force, it just slows down quickly and stops in the honey. And stops at some place which is not necessarily zero in general. Those are the three behaviors I want you to keep in mind. Now we're going to write down the field equation. Oh, before we do, let's imagine now the following scenario for our oscillator. Omega is not actually a constant. Omega varies now. It varies slowly. If it varies slowly at any given time, the behavior will be whatever it should be for constant. So omega varies slowly. It starts out large. Omega starts out large, and so it starts out in the oscillating regime. Omega, much bigger, let's say, than gamma. Restoring force strong, gamma small. What does it do? During the time, this is time, this is x, it oscillates. And if oscillates with the frequency omega. But now, and of course, if gamma, there's a little bit of gamma, so it mildly starts to decrease. Okay. Now gamma starts to get stronger. As gamma gets stronger, the frequency decreases. Remember the formula for the real frequency here has 4 omega squared minus gamma squared. So as gamma increases, the frequency starts to decrease. Eventually we get to the point where gamma is equal to 2 omega. Omega is decreasing. And then beyond that, it's overdamped. And so what it does, and at some point, it simply stops oscillating if omega goes to zero. If omega gets sufficiently small, fast enough, it will simply stop oscillating, not enough restoring force, and it will behave like this with no restoring force. So if we had an oscillator where we could control the restoring force and allow it to get smaller and smaller and smaller at a sufficiently rapid pace, we would see oscillations with time, we would see the oscillations slow down, and then we would see it just come to rest. And it would come to rest at some place. You'd have to calculate the equations of motion to find out where it comes to rest. And it depends on the initial conditions. That's the system we're going to be interested in, the damped harmonic oscillator with a time-dependent restoring force, and one that goes to zero. Okay, so what does this have to do with anything? To understand what this has to do with anything, we need to go back to the equations of motion of the inflaton field. Everybody remember the inflaton field? 3 cheers for the inflaton. Without it, the universe would be wrinkled up like a raisin. Or a prune, better yet, a prune. Okay, so what about the inflaton? The inflaton is a scalar field. It's a scalar field with a potential, v of phi. Remember, we thought about a potential which was very flat, with some energy density, and then suddenly a cliff. That's the form that the inflaton field, we don't understand why the inflaton field behaves like this. We know from observation that this is the way it has to be in order for it to, for things to work out. The inflaton field itself, this is phi, this is v of phi, and the motion of the field is very much like rolling down this hill, a very shallow, mild hill. It moves very slowly till it gets to the cliff, and then it falls down, and falls down to the bottom. So the universe is like a little ball rolling on this hill, where the ball literally means the value of the field at any time. All right, let's, for the moment, we're going to make an approximation. The approximation is that V is flat in here. V being flat means that V prime of phi is close to 0. Let's write down the field equation for a scalar field with no potential. The full equation of motion in ordinary flat space-time. What is it? It's the wave equation. It's the good old wave equation for a scalar field in empty space. This would be in ordinary space-time, not in inflating or expanding space-time. Anybody remember what it looks like? It's a second-order partial differential equation. It's a wave equation, and it looks like minus d second phi by dx squared, and then another term for y squared and another term for z squared. I won't write them. This is the wave equation, and we set it equal to 0 for a scalar field with a flat potential. If the potential were not flat, we would put on the right-hand side minus dv by d phi. But it is flat, at least approximately so. So let's ignore this. Now, but the universe is expanding. If phi was flat, meaning to say if it didn't vary from point to point in space, this would not be there, right? We'd have only this. Okay, the last two times we discussed the equation of phi in the presence of an expanding universe. I'll write down what it was. It was d second phi by dt squared. I called it phi double dot. But it was just a second time derivative of phi with respect to t. I'll write it as partial derivative. Doesn't matter, partial or ordinary derivative, if things don't depend on space. And do you remember what the second term was? Had a 3 in front of it. H. H is determined by the amount of potential energy here. And if it's constant, it's just a constant H times what? Phi dot, right? That's d phi by dt. And now, that's what we had under the circumstance that phi did not vary from point to point. Okay, but there has to be another term if phi does vary from place to place. In fact, that other term has to be such that if A is constant, if the scale factor is constant, then we should reproduce this equation, or an equation very much like it, with A being constant. So there's got to be another term in here, and I'm going to tell you what the other term is, and then I'm going to try to explain to you why it's that. Incidentally, H would be 0 if the universe were not expanding. So in a non-expanding situation, you don't have this at all. You would have minus d second phi by dx squared. So let's just try minus d second phi by dx squared. We might guess that that's the equation. That would not quite be right. Do you know why? Well, the real correct equation should involve the derivative of phi with respect to proper distance. Proper distance means measured, let's say, in some fixed units. Units such as meters, or better yet, light seconds. If there should be a speed of light here, incidentally, but let's leave it out. Let's work in units of light seconds, where the speed of light is 1. This would be correct if we were measuring x in standard units of light years or light seconds or whatever, but we're not. We're not. The actual distance between points separated by a given delta x is how much? A times delta x. The scale factor times delta x. So we can say ordinary lengths are delta x's times a. That means that this second derivative with respect to x squared is not the right thing here. It should really be second derivative of phi with respect to distance measured in standard units, and that means that there should be another a squared downstairs. 1 over a squared, and a times a little dx is an actual length. And that, in fact, is the right equation for a scalar field in an expanding universe. And in general, a is a function of time. A is a function of time. In the case of interest here, h is pretty flat, doesn't change much with time, but this is there, 1 over a of t.
Should that term be plus?
Hmm?
Plus 1 over a squared?
No, minus. Should match this minus here. Why do you think it should be plus? Who asked?
I asked that, I must be mistaken.
What's that?
I must be mistaken.
You are mistaken. Do you understand why there's a minus here? For a wave equation? Yeah. Okay, this is just this term, except rescaled with appropriate unit changes so that the unit of length, which should go here, is a times delta x. A times delta x is a little differential distance. That's our equation. And what I want to solve it for is waves. In particular, I want to solve it for a solution that varies with x. How does it vary with x? Like a sine wave or a cosine wave. In other words, I'll use complex exponentials, but it really just means sines and cosines. In other words, a wave which has the wave form that it behaves like e to the I kx. K dot x. X is a three-dimensional vector, and k is the wave vector. Times, now that's a funny looking thing. It doesn't depend on time. We expect our waves to depend on time. If this is the form, then we want to put a phi sub k of t here. Now, of course, there are many possible waves that can propagate. We should add up lots of waves, but later on we'll add up lots of waves. Let's just study what happens to a wave of this form. Okay. Let's plug this form into this equation. See what we get. d second phi by dt squared, well, the only thing here that depends on time is the coefficient out here. All right? So that's going to give us the second time derivative of phi sub k. Phi k second time derivative times e to the I kx. Times e to the I kx. Let's put the e to the I kx outside. Every term here is going to have an e to the I kx. All right, so this one will have phi double dot. How about this one? Plus 3h phi dot, right? Phi dot of t. And what about this one? Plus or minus? What happens if I differentiate this twice with respect to x? I squared gives you a minus 1, so you get plus k squared over a squared of t times phi sub k of t. Well, here we have the
A squared of t or a of t?
a squared. Thank you. Here we have the damped harmonic oscillator. Phi double dot, 3h phi dot, 3h plays the role of gamma. 3h plays the role of gamma, times a constant times phi. That's what we call omega squared. But with one new thing. Omega squared depends on time. And as the universe expands, omega squared gets smaller and smaller. If the universe exponentially expands, we can even say how a squared gets big, but we're not going to worry about it. We're just going to say a increases with time, and so the restoring force decreases. That's exactly the situation that I've either erased. Oh, here it is. It's exactly this situation here, where the restoring force decreases as a function of time, goes to 0 as the universe expands, and the result is exactly this kind of thing, where because the restoring force goes to 0, it doesn't get pulled back to the origin, it just winds up asymptotically at late times with some value of the field, some numerical value of the field that depends on the initial conditions, it depends on solving the whole equation set of equations, but it ends up with a number for phi for each k. There may be many waves. There may be waves of this wavelength, waves of that wavelength, waves going this way, waves going that way. If for whatever reason we started out with a complicated set of waves, each of those waves will first of all stretch. They stretch just by virtue of the fact that this x is not a physical unit, it's a stretched unit. So as the universe expands, the waves stretch out and they oscillate for a while. At first they oscillate, and then the oscillations die out and they come to rest, but they come to rest with some non-zero value of the field. For each k that's true. And so, but on the other hand, it's also true that each wave gets more and more stretched. So as measured, as its wavelength as measured in meters, gets longer and longer and longer, everything gets stretched out. And that was the whole purpose of inflation. To start with anything, stretch it out, and let it just stretch out. That would be the end of the story if it were not for quantum mechanics. Quantum mechanics has zero-point oscillations. Those oscillations can be thought of as just classical waves. Where did we write the formula for them? The zero-point oscillations of each oscillator means that in space there's an oscillating field for every value of k. Now, why don't we see it? Typically, the oscillation frequency is very large. Typically, we're in this regime here where the oscillation frequency of the zero-point oscillations of electromagnetic field or pretty much any kind of field are so rapid that we average them out and we don't see them. Okay? They're there. Okay? But look what happens here. The wave starts oscillating so that its time average is 0 in the beginning. We wouldn't see it, but then it slows down and eventually comes to rest with the field just frozen. That's the way you should think about these 0-point oscillations. The 0-point oscillations in the expanding universe go through this transition from underdamped to overdamped and then just settle down and freeze. Each one freezes. But it's important to know when they freeze. When they freeze means when do you reach this critical damping? So let's see if we can figure out at what time the critical damping happens. And the answer will depend on k. The shorter the wavelength, the later the critical transition will happen between underdamped and overdamped. Another way of saying it is the smaller the wavelength, the later the wave will get frozen and stop behaving with oscillations. Let's see if we can see how that's so. The critical transition between the two is at gamma equals 2 omega. So let's work that out. Gamma equals 2 omega. Now what is gamma? Gamma is 3 times the Hubble constant in the expanding universe, in the inflating universe. So gamma is 3h equals twice, and omega is k over a. Omega is k over a. That means that the transition happens when a is equal to 2k over 3h. I've just solved this equation here for a. I've divided by 3h, multiplied by a equals, now notice that the freeze out, it's not called freeze out, it's officially called exiting the horizon. Don't ask who's exiting, nobody's exiting. It's exiting the horizon, but it's just a set of words. The transition from underdamped to overdamped happens for a given k when the universe has expanded so that its scale factor is twice k over 3h. The 2 over 3 is not important. What's important is the k over h. The smaller k, the larger k means small wavelength. Large k means rapid oscillation. When k is large, then the freezing doesn't happen until a large a. When k is small, that's a long wavelength, it happens faster. Okay? Let's see if we can write it a different way. I want to write it a different way. I want to replace k by the wavelength. Let's replace k by the wavelength. We have a wave, it's a sine wave of some kind, and it goes, let's say, like sine kx. Now remember, x is not the thing that's measured in meters. X times a is the thing which is measured in meters. We'll need that. Right? But nevertheless, what is the wavelength in x that's associated with this oscillation, with this wave? The wavelength lambda is equal to 2 pi over k. Everybody know that formula? 2 pi over k? That's how far you have to go before the wave executes one oscillation. Or you can write it as k is equal to 2 pi over lambda. But now, is lambda really the true wavelength of this radiation? It's not the wavelength measured in meters or in light years. It's the wavelength measured in these artificial units that are expanding with the universe. If we want the wavelength in standard units, we want to put another A down here. A wavelength in X times A is a wavelength in true meters. So K is equal to 2 pi divided by the actual wavelength of the wave measured with a meter stick divided by A. Do I have that right? No. No, I don't. A upstairs. Yep. Okay.
Doesn't X go to AX?
Yeah, okay, this, let me, yeah. K is dimensionless, A and lambda is a length, A is a length. Yeah, this is right. Okay, so let's see if we can understand why. What are the units of K? What are the units of X? No.
So,
No.
unit of sort, right? That's just these grid units or whatever.
Dimensionless. They have no dimensions. They're just names of places. Okay? X is dimensionless, and K has to be dimensionless, and K has to be dimensionless. So to figure out where A's and K's go, K has to be dimensionless. Lambda is ordinary wavelength measured in meters, so this has units of length, and A has units of length. So this is right. This is right. K is 2 pi A over lambda. And that means we can substitute into here. Now, what was this point over here? Remember what this stood for? That's the scale factor in which the crossover happens from underdamped to overdamped. So let's put this in. This is equal to, let's forget the 2/3. K is equal to 2 pi, let's forget that too, A over lambda, that's K divided by H. So the crossover happens when the scale factor is equal to about, give or take a factor of pi's and 3's, A divided by lambda H.
A on both sides of the equation. You have A on both sides, but one of them's divided. Oh, that means lambda H has to equal 1.
The crossover happens when the actual wavelength of the radiation, when lambda is equal to 1 over H. Does that mean anything to anybody here? What is a distance which is 1 over the Hubble constant? It's actually probably, there's a speed of light in there, but we've set the speed of light equal to 1, and we'll continue to do so. Lambda is equal to 1 over H. Does that ring a bell? Okay, let me remind you what.
Is that where the expansion is faster than the speed?
That's where the expansion reaches the speed of light. Let's just check that. Hubble constant is defined so that distance is equal to so that velocity is Hubble constant times distance, right? That was a good old definition of the Hubble constant. Okay. Where, at what distance does the velocity go to the speed of light? That's when 1, the speed of light in our units, is equal to h times d. Or in other words, d equals 1 over h. That's the significance of h, if you like. D equals 1 over h, either d or h, is the distance out to the point where things are receding at the speed of light. You can call it the horizon, if you like. It's the distance usually called the Hubble the Hubble distance or the Hubble horizon. So what have we found here? We found that for each wave, here's the picture. You have a wave propagating. Let's put some meter sticks down here. These are meter sticks. They're not expanding with the background, but the wave is expanding. It started out with a small wavelength, and the expansion of the universe just expanded it. As the universe stretched, it began to stretch until its wavelength was equal, well, until its wavelength was equal to about a horizon size. Now, is this horizon size that we're talking about 10 billion light years? No, because we're talking about during inflation. During inflation, the expansion was so fast, the Hubble constant was so big that the Hubble horizon was a tiny microscopic size. But still, think about it as the horizon size of the universe at that time. It was expanding extremely rapidly with a very large Hubble constant. And therefore, this wavelength was a microscopic wavelength, but still it played the role of the horizon size at that time. And each time a wave that might have been present grows to the size that it is equal to this Hubble horizon size, then it freezes. Then it goes from oscillation to overdamped, and it gets it even a little bit bigger, and it stops oscillating altogether. It stops oscillating altogether because as the wave expands, the restoring force here, where's the restoring force? Here it is. The restoring force goes to zero. Okay? So that's the picture, that if you had an ambient population of waves, the waves would stretch until the wavelength got to be the size of the horizon, and when it got to the size of the horizon, it freezes. It no longer undergoes oscillations, it's just frozen there. All right, now, each one of these waves gets stretched. If there's only a certain population of them, eventually they'll all get stretched so much that they all just get, the field becomes uniform. Unless there is a source of new waves. Imagine now that as the waves stretch and become larger than the horizon, new waves come to take their place. I'll tell you in a moment where the new waves come from. New waves come to take their place so that as everything expands, a population of waves keeps getting created, and they get created with short wavelength. They begin life with short wavelength. They stretch, and eventually they reach the horizon size. They become frozen. Okay, where do these new waves come from? They come from the vacuum fluctuations. They're always, at every wavelength, let's say a wavelength of 1/10 of a centimeter, they're there. That wave then expands, stretches, gets frozen. But a new vacuum fluctuation is still there. That new vacuum fluctuation, which is still oscillating, but at smaller wavelength, expands, gets stretched, freezes. Then the next one comes, expands, freezes. The result is a population of waves that keeps coming in, and eventually leads to a picture where the field profile in space, the frozen field, the one that's not oscillating violently, the one that's not averaging to zero, consists of sums of waves of one wavelength, another wavelength, another wavelength, another wavelength, and the whole thing just makes a kind of random pattern of field. It's not really random. It is this pattern of waves on top of waves on top of waves, more and more of them coming in, exiting the horizon, and as they exit the horizon, they freeze. That's a population of waves that is ultimately coming from the quantum fluctuations, and which ruins the isotropy and the homogeneity of the, yeah.
I thought the waves freeze out at a particular point. Are they freezing out at a particular wavelength?
Yeah, they're freezing out at a wavelength. That's right.
Is that because h is exponential in time?
No, h, all right. If the potential is flat like that, at least while the universe is up on the flat part, h is constant. H is basically the square root of the potential energy. It's constant. So to a good approximation during this period, h is constant during this period when you're up on the top. Yeah.
Are these waves in some form of electromagnetic waves?
No.
Particle waves? What are we talking
The inflaton waves. The inflaton waves. The field which someday may or may not get discovered, but we're pretty damn sure it's there because this theory works to really, really good precision.
Is there a continuum of wavelengths? Or
Yes.
is it more
There's a continuum of wavelengths. That's right. There's a continuum of
So
wavelengths.
it's steps? It's not continually varying?
No, it's not. It's continually varying. It's continually varying, and if you really want to work out the details of what the shape looks like, you have to do a Fourier integral. The field is described by a Fourier integral, which is a continuous sum of waves, and each wave undergoes this process.
So is that continuousness due to an infinite universe, or if it's finite, don't you have only solutions, only discrete solutions? You know,
Yeah, yeah. If the universe was finite, you would have only a discrete collection. That's right. Yeah, yeah. However, they would be so closely spaced that yeah, no, that's true. Right. So this can be thought of as the picture for an infinite universe. Yeah. And it keeps pumping and pumping and pumping these short wavelengths in. They undergo this transition and then come out the other side frozen. Every time a wave gets to be of the Hubble length, it freezes. Another one comes and takes its place, not in the discrete sense, but in the continuous sense. And so the waves are sitting there in the universe of all different sizes, shapes, and orientations. Now, all of this takes place on top of something else which is going on. Very slowly but gradually, the field is sliding down this potential. That's classical, purely classical motion, just sliding down exactly as if none of this quantum fluctuation were there. On top of that, there's this quantum fluctuation noise. It's almost white noise. It's not white noise, but it's some kind of noise. Some kind of noisy, random fluctuations that keep populating and sitting on top of the classical motion. Now, none of this fluctuation is very strong, in fact. It's all quantum mechanical in nature. That means it has h-bars in front of it. It's a tiny effect. It's not a big effect. It's certainly in itself, the energy stored in these waves is not enough to explain the variations in energy density across the universe. Something else, I think we have time to just barely finish this discussion. So something else is going on, and what's going on has to do with as you slide down there and go over the edge. Okay, so let's talk about what happens when you slide down and go over the edge, and something rather dramatic actually happens. Let's first ignore the noise and suppose the entire universe simultaneously goes over the edge. Let's draw that. The horizontal axis here is phi, and the vertical axis is space. Not used to drawing space being vertical. Here's space. One-dimensional space, but use your imagination to put in a couple of more dimensions. At any given instant of time in that picture, the field phi has a certain value, and if we ignore the quantum noise, the value is the same at every position. It's just a field with a constant value, and that constant value is slowly sliding down the hill. All right, so at every x at any given time, let's say at a certain time, the field has a certain value. There it is. This is the value of the field at time t1. Let's put over here, here's the cliff. The cliff I'll represent this way. That's the cliff where you fall over the edge. What happens as time goes on? As time goes on, the universe rides slowly, slowly down that hill. So it moves from here to here to here until it gets to the edge. And when it gets to the edge, it all falls off the edge. What happens to the potential energy up there? It turns into particles and heat and other things. What happens to the expansion of the universe? It's less rapid because the energy density is less rapid. And in fact, it's just ordinary particles. It's no longer vacuum energy. It's ordinary particles. And what happens to ordinary particle energies as the universe expands? It dilutes. So after falling off the edge, two things happen. The expansion is no longer exponential, and the energy density dilutes. That's it. That's all. Except not quite. And the reason not quite is this noise. So let's think about the noise. The noise says that from point to point, the field is not the same at every point. It wanders a little bit. So the field at a given time might look, I'm not going to use dotted lines. Dotted lines are a little too hard for this picture. It may have a little bit of waviness into it. That waviness is this composite waviness formed from all of the quantum noise that got frozen. All right, so instead of being a perfectly sharp line here, where at every point of space the field is the same, at different points of space it wanders a little bit. Not much, not enough to account for anything very interesting. Think of the field at different points of space as a bunch of people walking down here, holding hands, trying to keep right parallel to each other until they get to the cliff and then go off the cliff. If they're really good at it, they'll all go off the cliff at the same time. But supposing there's a few who lag a little behind and a few who are a little bit ahead, and then as you go a little further away, a little bit of sloppiness, military sloppiness. Sometime I'll tell you when I was in the ROTC. Let me tell you, we were sloppy. So, right. All right. So they're going down, and the first guy, who happens to be a real hot dog, he's a little ahead of the others, and he goes whoop first. The other ones are left behind, right? And then somebody else goes over the edge, and then somebody else goes over the edge. But when the first guy goes over the edge, that means that this has shifted to a configuration where somebody's gone over the edge here. In that region of space, that defines a little region of space. Let's take that little region of space. What's going on in there? Well, first of all, what's going on in there is you're sliding down the hill. You're heating in there because that energy is being converted to ordinary particles and light and heat. And it's getting diluted because even though the universe may not be exponentially expanding, it's still expanding in a more ordinary way in here. And so the energy density is getting diluted. So we have some places now which are no longer inflating, meaning no longer exponentially expanding. They're expanding more slowly, but the energy density is diluting. Then a little bit later, the next guy comes and forms a little pocket. These pockets have expanded somewhat and diluted. Their energy density is less than the way they started. But then the next guy comes over the edge of the cliff. His potential energy gets dumped into particles in heat and light. And it has not yet diluted. It has not yet diluted. So the energy density here is going to be larger than the energy density in here. So there'll be some little pockets like this with higher energy density. Then the whole thing will evolve for a while. Everybody will grow a little bit. And the next group of soldiers will go over the edge and produce little pockets, even smaller pockets, with higher energy again. The result is going to be a very complicated fractal variation of energies. Something else, the slower, how does this effect depend on the speed with which you ride down the hill there? Well, the slower they go, the bigger the effect. Why? Because the slower they go, the longer the time interval between one guy going over and the next guy going over. The longer the time interval, the more dilution that's taken place before the... So in fact, the slower phi dot is, the bigger this effect is. What is the net upshot? The net upshot is a complicated fractal distribution of energy density, delta rho, that's the fluctuations in the energy density, divided by the average background energy density, which is present as a consequence of this complicated evolution, but it can be followed. In fact, it really can be followed throughout its history. And depending on the detailed nature of the parameters in the potential, it is not hard to make this delta rho over rho to come out to be the 10 to the minus 5 that's observed in the in both the W map and what is needed for a galaxy evolution to form those nice fractal structures that we saw in the sky last time. This theory has been turned into a highly quantitative, if you go and you look up W map, Google it on the Google, and you'll see all kinds of detailed curves that have been fit by one or two parameters that describe an entire range of different frequencies, different wave numbers, and really do nail this theory in place very solidly. One last point. Okay, so what does all this have to do with the map that we started with, the W map? The W map, which looks like this, with structure here and here. All right. What this process is making is it's making pockets, or what should we call them, blobs. Blobs within blobs, on top of blobs, of all possible sizes, shapes, with a particular characteristic distribution. It's not just totally random. It follows, the distribution does follow from the theory. And variations from point to point in space. Now we put ourselves somewheres. We're over here, and we look out. Remember, when we look out in shells. We look out to different distances at different times. And out at some distance, we see the surface of the place where the universe got opaque, where the radiation, microwave radiation, is coming from, and that's some distance out here. That's what we're seeing when we look at the microwave background. And notice that the shell describing this microwave, the origin of this microwave background, is passing through a variety of different energy densities. Where the energy density is large, let's say there's a large energy density over here, then the photons on their way in will be somewhat redshifted relative to the photons which are coming from a less dense place. The meaning of this is that when we look on the sky at the surface of the last scattering and we see all the structure, we don't see the structure. What we see is the structure projected, not projected, the structure as it exists on the surface of the last scattering. That's what this complicated map is. It's seeing exactly that structure. On the other hand, if we come into the interior here, away from the surface of last scattering, we are seeing the density fluctuations, which are the seeds of structure. These are the things which evolve by a combination of the mechanism we talked about last time. What was that? That was caustic formation. Also just gravitation. Gravitation starts pulling these things together. Galaxies form and so forth. So what's inside here, that's the evolution of that is galaxy formation. What's on the edge of visibility is the source of the microwave radiation, and that's what we see by WMAP. Yeah.
What point in time does that correspond to? I mean, in the age of the universe, what we see today? You know,
We see all sorts of things today. I see you.
no, but I mean the microwave background.
That originated about 13 billion years ago. You mean when did it form relative to what? Relative to, okay.
So we don't see all the way back to time zero because of the Hubble distance.
All right, okay, good. We fall off that cliff. The falling off that cliff happened at a very early time, and it was the origin of matter in the universe. The universe expanded. At the same time, we rolled down to the bottom. Everything that we directly measure takes place at the bottom, including the microwave background. Right. The microwave background originated a couple of 100,000 years after we fell off the top of the edge there. The universe cooled a lot. When it fell off the top of that edge there, the scales involved were hugely hot temperatures by our normal standard. The universe had to cool a great deal before it cooled down to the point where the recombination or the electrons and protons formed hydrogen atoms until the universe became transparent. That took a couple of 100,000 years. I forget the exact numbers, roughly 200,000 years.
So it's almost all the way back to the beginning.
200,000 years is a very short fractional time. Right.
Question?
Yeah.
The WMAP analysis also produced an anisotropy, a preferred direction. Does that fall out of this?
You're talking about the north-south. Yeah. I actually don't know what the situation is now with that, but nobody takes it very seriously. It's thought to be a statistical fluctuation. It's thought to be a statistical fluctuation and not.
That Longo's deep sky survey, where he's looked at the spiral galaxies,
Yeah.
and 7% of them, which is about one chance in a million, also line up with the axis of Eden. Not exactly, but close to it. So that's a separate.
Yeah, my understanding, the people who do the statistics of it don't think it's a statistically significant thing. I don't have a strong opinion about it one way or another. The problem is, with the universe, you can't really, certain things you can do statistics with and certain things you can't. For example, consider variations along here. There are small-scale variations. Let's say small-scale variations involving 1/10 of a degree. There are many small-scale variations involving 1/10 of a degree. You can do some statistics on them, and you can ask whether the small-scale variations like this are isotropically distributed. It makes sense to ask, and you can do it because you have many of them. On the other hand, if you think about a large-scale fluctuation, one that looks like a, maybe just an ellipsoidal or they're characterized by multipole moments, a quadrupole moment. There's only one of them. That happened only once. You don't get to do statistics on it. There's only one sample that you can draw out, which is a fluctuation which took place on large scale. So this is said to be cosmic variance constrained, which simply means that you don't get to do statistics on these large-scale variations. Of course, if we could look out beyond our horizon, we would then be able to see many, many large-scale variations of the same size pointing in different directions and so forth, but we don't get to look out that far. So all we get to see is one sample of what is called a quadrupole moment. The quadrupole moment differs from the average prediction by about a factor of 2. That factor of 2 is believed to be basically the imbalance between the north and southern part of the sky. And I don't know, it would be wonderful if it was something real telling us something. Most likely it's just
I think the anomaly is that the dipole, the quadrupole, and the octopole all line up.
it's not in the dipole. There is no dipole. Well, the dipole,
The quadrupole, the octopole, and the next one should be random, and they're
Right.
aligned.
yeah, look, you'll have to find some expert at the statistics of these fluctuations and find out what they think. Don't go to the press for it. Don't go to even the Scientific American. You have to go to the scientific literature because everybody else will tend to sensationalize it a little bit. On the other hand, it could be something real. The problem is there's no way to tell. You know, if you flip a coin 5 times, now let's say 6 times, and you get 4 heads and 2 tails, have you violated the rules of large numbers? Now, if you do that same experiment many times and you keep getting 4 heads and 2 tails, you say something's wrong with that coin. The coin has an imbalance. In the same way, if you look at this structure many times and you see the same thing, okay, then there's a problem. If you see it once, you can say, well, look, maybe something's wrong with the coin, or maybe it was just an unlucky event. And the point is, there's no way to do the experiment again. You're stuck with the one universe that we have, and that's where we are. Okay, I think we're finished for the quarter.
For more, please visit us at stanford.edu.